Right. Let's look at the limits of the equation of radiative transfer, some illuminating limits. Let's consider first the optically thin limit that happens when the optical depth is much, much less than 1. So if you start from the equation of radiative transfer, the optically thin limit would be when tau is much, much less than 1. So you see here that the exponential, you can Taylor expand it in this limit into 1 minus tau. So applying it to the equation of radiative transfer, this becomes, and because tau is much, much less than 1, you can remove this term, and this term. So you end up with the intensity is equal to the original intensity plus the source function times tau. Or if you want to write that in terms of the geometrical depth, the results show that in the optically thin case, the original result is unaltered, but emission is added. The emission is unattenuated, there's no absorption, and all the contributions from 0 to the full geometrical depth L or the full optical depth tau are added. The opposite limit is the optically thick limit, where tau is much, much bigger than 1. And if you consider again the equation of radiative transfer, e to the minus tau becomes 0, and what you have is simply I is equal to the source function. So if you have a constant source function, this becomes simply intensity is equal to the source function. In terms of geometrical quantities, this is the source function is equal to j over kappa. So if you multiply and divide by rho, you make use of the fact that 1 over kappa rho is the mean free path. This becomes then j times rho times the mean free path. Now this geometrical one is very enlightening. It shows that the contribution to the optically thick emission comes only from the last mean free path. And that makes sense. When you have optically thick medium, any photon produced anywhere else is going to be absorbed. And it's only the photons that are produced in the last mean free path that has a chance of escaping. So this is the intensity that you're going to see, only coming from this last mean free path. One example of optically thick emission is limb darkening. When you look at the sun, if you look at the center and if you look at the edge, you have different fluxes. The center looks brighter than the edge, and that is because the light that is escaping towards you from the center has less of a path to travel than the light at the edge. If you look geometrically, imagine that you have the light that you're seeing is the light that is escaping here from this blue area. And then to escape here from the atmosphere, it has to cross this path. So that's the light that gets to you. The light from this blue area to escape towards you from the limb has to cross a larger path, so it's more attenuated, and therefore it's going to look darker. That's what you're seeing here in limb darkening. Now the opposite, which happens in the optically thin case, would be limb brightening. So here is what it would look like. Say that you're looking at a planetary nebula from very up close. What you'd see then is an optically thin bubble. So this bubble here is homogeneous in brightness, but you're looking at the limb being brighter than the center, and that's because the center is less material emitting, and whereas at the limb you have more material emitting. So you may have a homogeneous cloud, right? But because now you're seeing here for less material, then and you're looking at the center, you have more material emitting. It's only light emitting from the shell, right? Imagine that this shell here in red is what is emitting. Here you only have this column that is emitting, and from the other side. And in the limb, you have all of this length here emitting, so it's going to appear brighter in the limb. That's what you're seeing here, limb brightening.